Hello everyone, I am Dr. Sathyanarayan Rao, and this is the third part of the video where actually in the first two videos I talk about the Sandy Loam keeps coming out on the top of my analysis. So we were working with a dataset of 677 paired observation. Each one had a field measured soil moisture value and its corresponding SAR backscatter value from the satellite in both L band and C band. So I highly recommend that please watch those first two videos as they walk through our data collection, feature engineering, and all our initial steps and initial results. So as a quick recap, here I show you a simple correlation plot between the HH backscatter and the field measured soil moisture. Why HH? Because it was the most important feature. So you have to watch those two videos before coming here. And in part 2 of the video, we actually checked that the high correlation of sandy loam and loamy sand was actually higher, was not due to the vegetation. So here in this figure what I have is the overall is the correlation of HH backscatter with the overall data. That means we lump all 677 samples that I had and its value is around 0.59. And to the right we have 5 soil textures with different values. Only the loamy sand and sandy loam is above the overall value. And if we look at if we split the dataset by radar band or bare soil and vegetated soil, it doesn't overtake the average value. The L band is almost same as the average value and it's better than the C band. That's what we see here. So it's not the radar frequency is not driving the correlation here, nor does the bare soil or the vegetation. If the bare soil had more signal and less noise, then we would have expected that it should be the most highest peak, but it's not so. So everything is below the sandy loam, which is at the highest 0.759. So from this chart, what is the key takeaway is that maybe the soil texture drives the backscatter soil moisture relationship. That's what this chart tells. And so next we actually ran some random forest modeling and saw how texture specific calibration could enhance our predictive accuracy. So next let's look at how our soil specific models actually performed against the generic random forest model. So in that generic model we used all the 677 samples that we had and R square was around 0.445, and as you see in the chart, every single texture except sandy loam actually falls below that average value or the baseline value, and we saw for sandy loam that it was a 34% jump, like 0.596. That's where it was the highest. So I have already explained back in part 1 and 2 of this video how we set up this random forest and what R square means here, and so please revisit those earlier videos. For now, the key takeaway is that the only sandy loam actually truly benefits from its own dedicated calibration of machine learning models. Every other texture actually does worse than lumping all soils together. So seeing sandy loam stand far above other candidates, we could think that high accuracy was simply because sandy loam happened to have more bare soil where radar can see moisture more easily without the leaves coming in between. And second, if most of the sandy loam in our data were actually under vegetation but they were very young plants with low leaf area index, that could also be a reason, but it was already proved that bare soil was not a high peak in the correlation in the earlier plot, but still these are valid reasons. This is what we walked through in the part 2 of this video. We did the LAI analysis, but here we will quickly recap the LAI analysis and the bare versus vegetated soil very quickly. So here we are actually checking whether vegetation cover, or more specifically the leaf area index, might explain sandy loam's performance. On the left you see the soil texture specific mean leaf area index for different soil. The sandy loam is at 1.72, or in other words, sandy loam does not seems to have an unusual LAI. It's okay, like it's not too low, and several other textures are actually just as green as the sandy loam. That's what we see in the mean LAI. Actually the loamy sand has the highest LAI, and it also had high correlation, which means that the leaf area index is not affecting the correlation. But the R square, the random forest R square for loamy sand was very low, below the average, not very low, but it did not exceed the generic model's R square, but the Sandy Loam does exceed, and it also has the highest correlation. So it's not due to that having more bare ground caused this is not valid. From this figure, loamy sand is fully vegetated, and also Sandy Loam is 70% vegetated. Actually, this was actually covered in detail in part 2. Actually, if you can revisit this segment to see. So with that ruled out, next we will see if Sandy Loam's own backscatter moisture relationship sees any difference between bare and vegetation sample. So here we see the next piece of evidence that when we split Sandy Loam into bare versus vegetated sample, the correlation between HH backscatter and the soil moisture is actually very different and opposite to what one would expect. On the left, only bare soil points were taken of the Sandy Loam, which was very special for us for so long, and it gave only an R of 0.38. On the right, we had vegetated points jump all the way to 0.743. It was actually a 95% increase in correlation. So what it means is that the Sandy Loam's performance was not due to because it was bare. In fact, the highest relationship, the best performance comes from the vegetated Sandy Loam. That is driving the strong SAR moisture link actually. So in the next we will see why this is happening by going a bit deeper on only focusing on the Sandy Loam under vegetation and comparing it with other soil that are also under vegetation. So now we have ruled out that bare Sandy Loam is not useful. It doesn't have any clue. So we need to zoom in on the vegetated Sandy Loam and see why it's different from the other soils. So after seeing that Sandy Loam was a special performer, I wondered that whether Sandy Loam might simply be sitting at some perfect soil moisture level, something like ideal soil wetness that makes the SAR backscatter look extra sensitive. To test that, I took out only vegetated plot for each soil texture and calculated the average field measured soil moisture and its standard deviation. And the result is what you see here. The clay is 27.5, loamy sand is 23.4, and everything is around 25%. We don't see that Sandy Loam is occupying some special soil moisture zone that could explain why it stands out. Its moisture distribution is just as broad and centered at the same level as other soils. So this means that the Sandy Loam performance cannot be explained by some perfect soil moisture level. It's not explained by leaf area index or the bare soil. So next we will see if it could be explained by some intrinsic signal properties like the sensitivity of the backscatter as compared to the soil moisture changes. So far we have ruled out that the vegetation or leaf area index is not the reason why Sandy Loam is stood out, or even the soil moisture level. So everywhere all the soil seemed similar. So what we did here was we isolated only the vegetated samples from all the soil texture. That means we drop any bare soil data points. The goal now is to see how the satellite backscatter responds to moisture when there is some vegetation. This actually avoids the bare soil effects, because the vegetated Sandy Loam was the one that gave us the high correlation. So once we have the vegetated plots for each texture, we fit a linear regression, a simple straight line, a model that fits a simple straight line between the field measured water content, which or the soil moisture, which I write it here as VWC, and the HH backscatter from the satellite. So here I show the mathematical form in the point number 2, where VWC is beta naught plus beta 1 times the HH backscatter plus a small epsilon. So here beta 1 is the dielectric slope. It tells me how much soil moisture changes for each 1 decibel change in the HH. In other words, it's the sensitivity. A big slope means that HH moves a lot when soil gets wetter or drier, whereas a small slope means HH hardly notices any change in the soil moisture. That's what it simply means, the model that I show in the step number 2. And now we know that we have the slope as well as we can compute the spread of the HH simply by calculating its standard deviation. The spread of HH values within each texture tells me that if HH barely moves a tiny standard deviation, there is not much for the machine learning model to learn from. On the other hand, if the HH value has a large standard deviation, it swings wildly, then radar is giving us a lot of information about the moisture that a random forest can find this pattern. So the spread is very important. So a high spread means machine learning model can learn a lot of details which we cannot figure out. So if we combine these two, like the slope, how sensitive the backscatter is to the soil moisture, and the standard deviation, we can call it as the information proxy, which I call it here as IP, is the dielectric slope times the standard deviation of the backscatter. We can think this IP as how much useful information the radar backscatter carries for that soil texture in the vegetated zone. So if a texture has a steep slope but almost no spread, then the proxy is always small. It's not a usable signal. If it has a huge spread and almost zero slope, it's a flat line. Again, it's small because the radar varies, but not in a way linked to the moisture. Maybe it's noise. So if both slope and spread are fairly large numbers, we can say that this is the information. And we want to see if this information is high for the Sandy Loam, and that's why we are seeing Sandy Loam perform better. That's what we are going to see in the next few slides. So to understand our concept, before I show you the real results, I made up a simulated example to show a good soil from a bad soil from our information proxy concept. This will help us understand why some soil gives a better machine learning model or a high correlation, like in our case, the Sandy Loam. Think of this like a simple cartoons, not actual data. They are just here to explain the idea. On the left, you see a good soil example. The little red dots slope upward sharply as the soil moisture increases. The slope, you see the linear fit here. A small change in the backscatter on the x-axis matches with a big change in the soil moisture on the y-axis. So that steep line is a sign that radar really feels the soil moisture content. You also notice that the backscatter value is spread across the several decibels, if you see the green arrows here on the left hand side. Because both slope and the points cover a wide range, the standard deviation of backscatter, there is plenty of information for the machine learning model to learn from. So maybe in our work, the Sandy Loam behaves very much like the left panel. It could have a steep slope and like a high beta 1 and a broad backscatter range. On the right hand side, you see a bad soil example. Maybe it could be like clayey ground. Here the data points hardly move up or down as the backscatter changes. It's almost a flat line. The slope is very flat. That means the radar will actually barely respond to any changes in the soil moisture. And you also see that the backscatter values sit within a narrow range. This combination of actually a low slope and almost little spread means that there is no information in the radar signal. So our information proxy on the right hand side will be a very low value. That means the machine learning performance will also be low. But on the left hand side, we have a high information proxy. So here is the actual data for our 5 soil texture. These are actually our real results. And on the x-axis, we see the information proxy, which we have defined as the slope or the sensitivity versus the standard deviation, as we saw in the earlier slide. But here we used only the vegetated samples. On the left y-axis, we see the R square both from our linear regression as well as from the machine learning model, the random forest R square. So here the circle is the linear R square from the linear fitting, where we find the slope and the random forest R square is also shown here. Just look at the Sandy Loam, which is right up in the right extreme corner. Its information proxy is 9.8, by far the highest of any soil texture. It combines a steep dielectric slope with a wide HH backscatter standard deviation, and as a result, its R square is 0.6, around 34% better than a generic model. And even the linear fit R square is the strongest among the other soil texture. And also the Sandy Loam It means that it has the most useful signal from the information proxy, the highest information proxy that we have. Just compare it with the other soils. The loamy sand also had a high R, but it did not perform better than the generic model because its information proxy is almost 4.8, almost half of that of the sandy loam. And if you see the others, clay, sandy clay, and other things, it all sit near the left. You see the information proxy is 2 to 6, something like that, here in the picture. So it means that information proxy, the way we have defined, translates to a strong machine learning performance. Sandy Loam ends up having the highest information proxy, and that's why it's a clear winner. It has the highest dielectric sensitivity and plenty of signal variability with the product which we have defined as the information proxy here. So the machine learning model can actually learn to predict moisture accurately in sandy loam case. So by contrast, the other texture with low slope or narrow backscatter, which means low information proxy, simply don't carry enough information. So as a conclusion, what I want to say is that if our information proxy is large, please go ahead and tune a soil-specific random forest model or any other machine learning model. You will get a better accuracy over a generic model. If it's a small, like if we have a small information proxy, we can stick with the generic approach that gives a better result. So lump all the soil texture and run a generic machine learning model. So this one plot alone gives us a roadmap for deciding when and where we should use machine learning for satellite-based soil moisture retrieval. Thanks again to Professor Shekhar Muddu for very useful discussion and the reward project for supporting my data collection. And thank you all for watching. I hope we will be publishing this work soon in a journal